and do 1.7. So this is on something called inverses. And let's just run through a couple of these ideas. So it says we've learned that a function is a mathematical rule that produces a set of ordered pairs. So we plug in an x and we get out a y. Okay? And what that means is each x corresponds to only one y value. Okay? And that's what it meant to be a function. We didn't want to plug in a 2 and get out a 3 and a -7. We only want one answer out, and we talked about the vertical line test and all that sort of stuff for a function. And it says, given that f of x is x plus 2 and g of x is x minus 2, it says find the following composites. Okay, so we're going to find f of g of 5. So I'm going to take 5, and what do I plug it into first? I'm going to plug it into g. So I'm going to take 5 and plug it into g. So if I do that, let's see, 5 minus 2, that's going to be 3, right? So then now I need to find f of 3. So if I plug a 3 in here, I get 3 plus 2, and I end up with, what's my final answer? 5. Okay, so f of g of 5 is 5. Let's do g of f of -4. So if I find f of -4, that's going to be -2. So I'm going to take -2, plug it in here, and I end up with -4, right? So g of f of -4 is -4. Okay? Now let's find the rules in general. So let's start off by plugging in x into g. So I'd get x minus 2. And then let's take that and plug it into x plus 2. So if I wrote this down, this is going to be f of, and f of something is that something plus 2. And what am I plugging in here? I'm plugging in x minus 2, right? And when I simplify that, what do I get? I get x. So f of g of x is just x. Okay, let's do it in the opposite order. Let's take f and plug it into g. So g is something minus 2. And that something that I'm plugging in is x plus 2. So if I simplify this, I get g of f of x is just x. So how are those functions above related? Could we take a guess at how they're related, especially since the name of this section is inverse functions? How are those functions related? They are, okay, they're inverses. Okay, so they are inverses of each other. Okay, so when we talk about inverses, they are a really key idea in mathematics. We're always learning how to do something, and then we learn how to undo it. Okay, so when we talk about inverses, okay, don't think of it in terms of they're the opposite of each other. Okay, that has a different type of meaning. A lot of times opposite means the negative of. Inverse means they undo each other. Whatever one function does, the other one undoes. So for example, we have add to and subtract to. Those operations are inverses. Okay, but some other examples would be if I times by 2, what's the inverse of timesing by 2? Dividing by 2. Okay, and that goes both ways. The inverse of dividing by 2 would be timesing by 2. Okay, what's the inverse of cubing? Cube root. Okay, cube root. Okay, so we're already familiar with a lot of things like that. The opposite of adding is subtracting, or what undoes adding, subtracting. The inverse of multiplying is dividing, and so forth. We've got lots of inverses. Okay, and you may be familiar with this type of notation, maybe not, but the notation that we use for a function. So say we're given the function f. The way we indicate that we're dealing with the inverse of that, or the function that will undo whatever f does, is we use this type of notation right here. Okay, now that's not f to the -1. Okay, that means f inverse. Okay, so that exponent is what looks like an exponent is not an exponent. Whenever we put a -1 above a function, it means the inverse of that function. Okay, so if I had the function g, we'd indicate the inverse as g inverse of x, and that's how we say it. Don't say g to the -1 or f to the -1. Say g inverse of x, or f inverse of x, or q inverse of x, or whatever the function name happens to be. Okay? So let's take a quick look kind of visually at what's going on here. So what we normally do is we take an x and we plug it into f. What comes out is whatever the function value is, f of x. We then plug it into an inverse function that undoes that, and we end up with the exact same function value that we had to start with, or the exact same x value. So this one does something, and its inverse undoes whatever was done. And it may be really complicated. Some of the ones that we're going to deal with today are pretty darn easy. Okay, the one that we did up above with adding 2 and subtracting 2, that's pretty darn easy. Okay, but let's take a look at some very simple inverses, and let's just show kind of numerically what would happen here. So let's say I plug in a 5. If I plug in a 5 into the function 2x, what comes out? 10. Okay, what would its inverse be? What would the inverse of timesing by 2 be? Dividing by 2. So its inverse would be dividing by 2. And what happens if I plug a 10 into x over 2? I end up with 5, right? So I started out with 5, did something to it, then undid that, and I end up right back at 5. Okay? So those are inverses of each other. So let's take a look at this one. What would the inverse of x minus 4 be? X plus 4. So let's pick a number. Brandon, pick any number you want. Be nice to us. 3. Take a 3. Let's plug it into this function. If I take 3 and subtract 4, what do I get out? Negative 1. If I plug a negative 1 into this inverse function, negative 1 plus 4 would be 3. I get right back where I started. Okay? And again, like we were saying just a second ago, what's the inverse of the cubing function? Cube root. So let's put that right here, and let's pick a number. Sarah, pick any number you want. Now, is 8 a good number? Was Sarah pretty nice to us? Sarah was pretty nice. So let's plug in an 8. 8 cubed is a pretty big number. Let's see, 64 times 8. Throw that in your calculator. It's a little on the big side, but we can deal with it. What is it? 512? And what happens if I take the cube root of 512? I get right back to 8, don't I? Okay? So these are inverses. Whatever one function does, the other function undoes that. So we get right back where we started. And the most generic way to show that is start with an x, plug it into a function, you're going to get out whatever that function value is, plug it into the inverse, and you're going to get right back to x. You're going to get right back where you started. Okay? All right, any questions? Okay, this book shows you how to do something kind of interesting. You can actually figure out, for very simple functions, you can kind of intuitively kind of just go through and think about it for a second and figure out, hey, I know what the inverse would have to be for this. And the way we do this is we kind of go through and we figure out, well, if I plug in a number, what gets done to it and in what order? So we're going to make a list of the operations. So let's take a look at this one right here. Oops, up here. What's the first thing that gets done when we plug a number in? Times by 2. So let's write times by 2. That's the first thing we do. After we times by 2, what do we do next? Subtract 5. Okay? Now, does it make sense that if you were going to undo those two operations, that you'd want to undo them in the opposite order? So you do this, then this. If you're going to undo those, you'd want to undo them in the opposite order, right? Okay, so I'm going to take a number, and the first thing I'm going to do to it is I'm going to undo subtracting 5. So what would we do? Add 5. Okay? And how do you undo timesing by 2? Divide by 2. So we think that this is the inverse. If that's f, then this is the inverse. Okay? So we've shown that using the correct notation. Okay, let's take a look at this next one. So we've got the function g of x. It's x minus 1 divided by 4. Let's make a list of what goes on here. When I plug in a number, what would be the first thing I do to it? Subtract 1, then what? Divide by 4. So if I'm going to undo those and figure out what the inverse is, then G inverse of X would be, I'd want to undo dividing by 4 first. How do I undo dividing by 4? Times by 4. So I'm going to take whatever the number is that I plug in, I'm going to times it by 4 first, and then I'm going to undo subtracting 1, so I'm going to add 1. So those are the inverses. Okay? But it would be really nice if we could say, you know what, we were just kind of thinking our way through it. We were just kind of guessing and checking on this. It would be nice if we could know for a fact that they do indeed undo each other. Okay? So we can verify that functions undo each other by finding their composites. In other words, plug the function into its inverse or the inverse into the original function. And they should do what to each other? They should, I heard the word cancel, I'll take that. They should undo each other. Or in other words, we should be able to start with X, do some math on it, undo that math, and what should we end up with in the end? Should end up with an X, okay? Just like we did right here, okay? So let's figure out what the composites are of each one of these. So here's what we're going to do. I'm going to do F inverse of X. The original function is 2x minus 5, so I'm going to have 2 times something minus 5. And what is that something that we're plugging in? What did we guess the inverse was? X plus 5 over 2, right? X plus 5 over 2. Let's simplify this. 2 times this stuff, what happens? 2 over 1, I can cross cancel those, so I end up with x plus 5 minus 5. These undo each other, so I end up with x. Are they inverses? Yes, they are. I started by plugging an x into the inverse function. I took that answer, plugged it into the original function, and I'm all set to go. Okay? Any questions? It shouldn't matter what order we do this. It shouldn't matter whether we plug the inverse into the original function or the original function into the inverse. So on this one, let's do G inverse of G of X. Let's do that. G inverse is right here. It's 4 times something plus 1. And what is that something that we're plugging in? X minus 1 over 4. Same thing happens. 4's cancel. X minus 1 plus 1. We end up with X. So they do undo each other. Okay? Any questions so far? Okay, so if you take a look at the notation here, what we've been doing is actually a test, kind of a way where we can tell or verify whether two functions are inverses of each other. So you can do f of the inverse, or f inverse of the original function f, and regardless of which way you compose these functions, regardless of which way they are ordered, which one's the inside, which one's the outside, because they're inverses and they undo each other, if you start by plugging in an x, what should you get out once you're done simplifying? You should get out an x, okay? All right, and then the last thing on this page, which leads us to an interesting result, which may be something that you've seen before, is the fact that we can actually check inverses kind of graphically, especially if we've got a pretty decent graph. And this is the idea behind this. So I want you to think about this for a second and why this would have to be true. So let's run through this statement. We'll read it pretty slowly and think about it for a second. If we put a into a function and we get out b, so put in a, get out b. It says blank would be on the graph of the function. What goes in there? AB. Okay? No problem there, right? If a point works in the equation, it's on the graph. If it's on the graph, then it must work in the equation. Okay, take a look at that next sentence, though, and this is where the thinking is required. This one says if we put b into the inverse. Okay, now notice, this was the original function. Now we're talking about the inverse. If I put b into the inverse of the function. So instead of starting with a, putting in a and getting out a b, I'm now going to work with the inverse, and I'm going to put b into the inverse. So let's think about that for just a second. Don't say anything out loud. If in the original function I put in a and get out a b, and then with the inverse I put in b, what should I get? Think about that for just a second. Raise your hand if you know. Raise it up high. Okay, about a third of the class, not too bad. Okay, think about what these two functions do to each other. This one does something. Whoops. This one does something, and this one undoes whatever that original one did. Okay? So here, if I plug in an A, I get out a B. On this one, if I plug in an A on the inverse, Logan, what do I get? Well, let's see. If I put in a B, that would be this coordinate right here, BA. Okay? So, does that make sense? Put in an A, do something to it, get out a B, take that B, put it in its inverse. Here's where we started, and here's where we end up. So do something to get to here, plug that in here, and get out an A. See how these undo each other? Okay, does that make sense? Okay, well, if you flip the page over, that gives us a way of graphically checking whether or not they're inverses of each other. Okay? So let's think about what this would mean as we look at these diagrams here. So here's a function right here. It's the inverse of f. So the original function is 2x plus 3, which we could graph. It should be 2x minus 3. And the inverse is 1/2 x plus 3, and that's in parentheses. So it looks like this. And what I'd like you to notice is, on the original function, let's take notice of this point right here, 2, 1. Look what's on its inverse, 1, 2. So if the original one was A and B, this would be BA. Let's take a look at this one right here. If 0, 3 is on, 0, negative 3 is on the original function, what should be on its inverse? Just switch them. Negative 3, 0. Okay? So you can tell that they're inverses of each other because you can take these corresponding points and just switch the coordinates. What used to be an x is now a y. What used to be a y is now an x. Make sense? Okay, let's take a look at this one right here. This is the square root function. This is x squared, not the entire graph of x squared, but take a look at the points. Okay, here's a point 1, 1. What happens if you switch 1, 1? You get 1, 1. It stays the same, right? What if we take 4, 2? 2, 4. 9, 3. 3, 9. Do those points look familiar? Okay. And what do we notice about those inverse functions and the line y equals x? They're symmetric about that line. You could fold it along this line. So in other words, they are symmetric, or they are reflections across the line y equals x. Okay? So if you ever want to graphically look at two functions and see whether or not they're inverses of each other, they should be reflections across the line y equals x. Okay. Raise your hand if you've seen that before. Inverses should be reflections across the line y equals x. Okay. About a third of you, so some of you have seen this before. Okay. Any questions so far? Okay. Well, the interesting part about that the fact that they're reflections across the line y equals x, x changes for y. So what used to be an x here is now a y here. What used to be a y here is now an x there. Okay? Gives us a way of telling whether or not we can look at a graph and tell whether or not it has an inverse. And it also leads us to how we can find inverses, not using that kind of intuitive, informal approach, but actually going through and mathematically figuring out what the inverse is. Okay? Which on some problems can be fairly complicated. Okay? So let's take a look at this one right here. And let's say I wanted to find the inverse of this graph. I'd have to reflect that across the line y equals x. So let's take this point right here, which is 2, 4, and this point right here, which is negative 2, 4, and this point, which is negative 1, 1, and this point, which is 1, 1, and 0, 0. And let's reflect those across the line y equals x. In order to reflect those, what do I do with the coordinates? Switch them, right? So this one is not going to be 2, 4 anymore. It's going to be, hello, 4, 2. Thank you. Okay. Thought I was talking to myself there. 4, 2. Okay. Let's see, 1, 1, that's going to stay the same. 0, 0, that's going to stay the same. Okay, what does negative 1, 1 correspond to now? 1, negative 1. Okay, and negative 2, 4? 4, negative 2. Okay, and let's connect these. Okay, and take a good look at this. If this is the function, is there any problem with saying that that's the inverse of the function? What's that? Okay, the inverse of this is not a function, okay, because it doesn't pass the vertical line test, okay? So this wouldn't work. This is not a function. So if I take x squared, it doesn't have an inverse. And yet we think, well, wait a minute. We've been solving like squared equations, quadratic equations, by taking the square root of both sides. We can undo that, okay? Well, in order to do that, we have to do something called restrict the domain, okay? But the point, at this far is, we can tell whether or not a function has an inverse, okay, by whether or not it passes the horizontal line test. So think about it. If the original function doesn't pass the horizontal line test, then when we reflect it across the line y equals x, and when x gets switched for y, when we switch those two coordinates, this one's not going to pass the vertical line test. Okay? So you can look at a function and tell whether or not its inverse is also a function by just checking to see whether or not it passes the horizontal line test. So let's take a look at this one right here, and the question is simply, which of these functions have inverses that are also functions? So if we reflected it across the line y equals x, I'd have a function. And we can tell that because, does this pass the horizontal line test? Yes. So its inverse would pass the vertical line test. Does this one pass the horizontal line test? Nope. So its inverse would not be a function. How about this one? Nope. Again, how about this one? This one is a yes. And how about this one? Okay, now take a good look at this one. Let me blow this up right here. What does that look like? Yeah, that looks like half of a parabola. So this is what we've done here. Instead of using the whole thing, I just use part of it. I do what's called restricting the domain. Normally the domain for the x squared function is going to be from negative infinity. I'm restricting it from 0 to infinity. And by just using this half of the parabola, I made it so it passes the vertical line test. So if I reflect it across the line y equals x, it will pass the vertical line test. Okay? And we're not going to worry about that a ton in this class, but just realize it is possible to restrict the domain so that you do have an inverse function. Okay? Any questions so far? Easy enough? Okay. Then we've got just a little bit more to do. If we have something that's more complicated as far as a function goes, and we still want to find its inverse, that little technique of listing what the operations are and what order we do them in gets a little bit complicated. Okay? It gets pretty hard to do. Okay? Now, you don't have any that are ridiculously difficult, but we do have some that we'd want to know how to find the inverse if it were more complicated. So here's the idea. We take advantage of the fact that when we do the inverse, what used to be an x gets switched for a y, and what used to be a y gets switched for an x. So we've got a quick little two-step process for finding inverses. Okay? One, we will switch the x and the y, and then we'll solve for y. So switching the x and y takes care of the order. Okay? We did something, now we want to go the other direction, so we're going to switch the x and y, and we're going to solve for y. So let's take a look at this one right here, and I realize we've had something like this. In fact, I think this is one that we did earlier, but let's just verify what the inverse is. So remember, y is the same as f of x, so I'd write it like this. So there's the original function. Okay, that's the original. And now I want to find the inverse. So I'm going to switch the x and y. So I'm going to write x equals 4y plus 1. And then I just solve for y. So I'm going to move the 1 to the other side by subtracting. Then I'm going to divide both sides by 4. So I get y equals x minus 1 over 4. Isn't that what we found it was before? Okay. Now, I also want to indicate that in the proper way. So I'm going to write that g inverse of x is x minus 1 over 4. Or if I wrote it in a form where I could graph it, this would be 1/4 x minus 1/4. Okay? So here's the inverse. Here's the original one. We're saying those two are inverses. And then the instructions say we should graph this on the same set of axes and see if they are reflections across the line y equals x. So let's go ahead and do that. We'll do the original one first. So this one crosses at 1 and has a slope of 4. So we're going to go up 4 and over 1, down 4 and back 1. So the graph looks something like this. This is the original function. This is g. And then let's graph its inverse. Crosses at negative 1/4, so about right here, and has a slope of 1/4. So a little bit careful on this with the fractions. I'm going to rise 1, that's going to be just under 1, okay? And I'm going to go over 4, so that would put me about right here. If I go down 1, that would just put me a little bit under negative 1, and then I'm going to go back 4, so that's going to put me about right there. And then I draw a line connecting those, and this is g inverse of x. And does it look right? If I tilt my head just a little bit and I draw that line y equals x, do they look like they're reflections across the line y equals x? They do, okay? And we could kind of belabor the point just a little bit and really make sure that we got this right. Can somebody tell me what point this is right here? It'd be 1, 5, right? Is that on this graph right here? So 5, 1, does that look about right? Okay, could we plug it in and check and see? If I plugged in a 5, minus 1 is 4. 4 divided by 4 is 1. So plug in a 5, you get out a 1. So, whoops, let me change colors here. So this is 5, 1 right there. Any questions? Sure? Okay, can I slide this over? Okay. We're going to do this one in a slightly different order. I'm going to go ahead and graph this one, and everybody should be able to graph this. You might have one like this on the test on Friday. You should know what this looks like. This is x cubed plus 1. So we made the shape, and then we added 1. What does adding 1 after we make the shape do to the graph? Up 1, right? So it's going to cross right here, and then I'd go over 1 and up 1, back 1 and down 1. Over 2 and up 8. So that's going to put me up here at, let's see, 2, 4, 6, 8, about right there. Okay, this point would be 2, 9. And I'd go back 2 and down 8. So that's going to be down 1, 2, 3, 4, 6, about right there. That's going to be negative 2, negative 7. And the graph looks something like this. Okay, will that have an inverse that's also a function? Will this have an inverse that's also a function? Peyton says yes. Brandon says yes. Peyton, why is it yes? Passes the horizontal line test. So when I reflect this across the line y equals x, it will pass the vertical line test. Okay, everybody watch, please. This line right here is the line y equals probably 6 or 7. Okay, if I take that and reflect it, it would be this line right here. If all the x stuff gets switched for y stuff, this is going to be a vertical line. It's going to be x equals 7. Okay, see how the x's and y's change? Horizontal, y equals a number. Vertical, x equals a number. See how that works when we reflect it? Okay. So let's go ahead and find the inverse. I'll change colors here. So I'm going to write the inverse down this way. This is the way I'm going to find it. I'm going to write x here, and I'm going to write y cubed plus 1. What did I just do here? Switch the x and y, okay? Wherever there's an x, I put a y, and f of x is the same as y, so I put an x right there. Make sense? First step in solving, what do I do, Sarah? Subtract 1, so we're going to subtract 1 from both sides, so this is x minus 1, and then this is going to be y cubed. And then Noah, how do I get rid of the cubing? Cube root. Take the cube root of both sides. Now, do I have to be careful with the cube root about pluses and minuses and domains and stuff like that? Not with an odd root. Okay, you can plug any number you want into an odd root, and we're fine. So the inverse is going to be the cube root of x minus 1. Now, did we draw the cube root function? I don't think we did. The cube root function looks like this. It's kind of like the cubing function flipped on its side. I mean, they're inverses. They're reflections across the line y equals x. It's going to look something like this, but can somebody tell me what the minus 1 would do to this graph? Change the x before we take the cube root to make the shape. Hop. Shifts to the right 1 unit. So we're going to take this graph and we're going to move it 1 unit to the right. And these are the points that it's going to go through. It's going to do something like this. Okay, that's bad. So if this is f inverse. Does it look right? That point right there is 1, 2. Is this point right here 2, 1? It is. Plug it in. 2 minus 1 is 1. Cube root of 1 is 1. Okay? Any questions? Easy enough? Okay, let's take a look at this last one. And can somebody tell me why is this restriction needed? Yes, Lynn. So its inverse will remain a function. Okay, this is, you could kind of think of this as like a one-piece piecewise function. It looks like this graph right here, which is x squared plus 1. We move that graph up 1 unit, so it's going to look like this. But we only use the part of the parabola that is on the right side of the y-axis. So we're only doing the domain from 0, including 0, all the way to infinity. And what that does is we're going to remove this side right here, because if we left that in there, it wouldn't pass the horizontal line test. Therefore, its inverse wouldn't be a function. It's not that the original problem isn't a function. It's that its inverse wouldn't be a function once we reflect it across the line y equals x. Okay? So this is the point 0, 1. This one right here is easy to find, 1, 2. This one right here is also relatively easy to find. It's 2, 2, 5. Okay? We're going to find the inverse. Okay, the inverse would be x equals y squared plus 1. Move the 1 over, x minus 1. And how do I get rid of the squaring? Take the square root. So f inverse of x would be the square root of x minus 1. And this should look really familiar. We know what shape that is. We also know, Sven, what does subtracting 1 from the x before we take the square root to make the shape, what does it do to the graph? Which way? To the right 1 unit. So we'd normally have a graph that looks something like this. We're going to take that graph and move it 1 unit to the right. So it's going to go through these points right here. Same shape. Okay, nothing changes about the shape. We're just moving where it is. And this point right here, 1, 0. This one right here, 2, 1, and this one right here. Five, 2, right? Okay. Any questions? You sure? All right. Holy cow. We're done 10 minutes early. You've got time to work on the assignment. That's pretty cool.